Where we left off on yesterday, talking about the E2 elimination, and the last thing we talked about was this geometric constraint that forces the E2 to adopt a certain geometry in order for it to happen, right? And really, I mentioned it, but I didn't really go into detail about it. It's really a consequence of orbitals overlapping, right? So the orbitals in this CH bond right here, they need to overlap with a certain set of orbitals in the CI bond, or the bond between that adjacent carbon and the leaving group. And if those don't overlap, then the electrons can't be shared to make that pi bond, and then you can't force out the leaving group. So with that being said, let me see. We talked about Zaitsev's rule. We talked about the alpha protons. We talked about the biomolecular nature of the reaction, that it's a two-term rate law. And so even with that, we need to think about what's the day? 14, man, this month is flying by. We need to think about the energy diagram, right? So for the E2, the rate determining step is concerted. Right, so what that means is that there's only one, just like the SN2, you go from reactants to products through a transition state with no intermediates. Right, so the E2 doesn't have any intermediates, and it goes, again, reactant straight to the product. And the rate, this all is all concerted, and this is the rate determining step. Just like in the SN2, the rate determining step, everything is happening simultaneously. It's the same thing for the E2. Really, I'm not sure if there's anything left to discuss regarding that. So we talked about Zaitsev's rule, we talked about, and I sent videos out finally. I apologize for the delay on that, but I've been super swamped over in Kresge. But also in the videos, it talks about the different types of bases that you'll see. Something like KOH is one of the common bases for E2, right? But you also can have so KOH is one. You could have an amine base. Terpbutoxide is also a good base. Normally the counter ion is potassium. And with the bases, I think I said in the video, the more bulky the bases are, then the better they are for proton transfer, right? Big bases make bad nucleophiles, if that makes sense. So the terpbutoxide is an excellent base because of its steric bulk. So picking off a proton is much easier than actually being a nucleophile and going and attacking an electrophile wherever the leaving group is. So yeah, so we'll talk about some E2 reactions today. I want to now shift gears and talk about the E1 reaction because it's a little bit different. It follows, as you can probably surmise, it follows a similar pathway to the SN1. We'll put it on a sheet. It follows a pathway that's similar to SN1. Right, so with the E1, you have tertiary or secondary carbons, right? Protic solvent, just like the SN1. So there's really not a whole bunch of new information to remember because the E1 and SN1 are identical up to the either the final step, which is either a substitution or an elimination. So they are identical. So everything that favors SN1 favors E1. So tertiary carbons, what does it mean if when we talk about in terms of the SN1 reaction, when we talk about tertiary carbons, why is that important? What happens in that mechanism that where a tertiary carbon would be favorable? What happens in the mechanism, in an SN1 mechanism? Doesn't it go through a carbocation intermediate?
Yes.
Mm-hmm. So the E1 is, again, if it follows the same pathway, that's why tertiary carbons are favored, because it's going to go through a intermediate. So we're going to go through the arrows for this. I'm just going to put the product in for now, just like we did up top. Right. This is unimolecular. That's what the 1 is in E1. What does that mean? We talked about it Wednesday. If I say that the reaction is unimolecular, what can we draw? What information can we draw from that? Anybody? What can we draw from the fact that it's a unimolecular reaction?
That it just deals with one molecule.
Exactly. And it's the substrate. So we can say that the rate determining step, just like SN1, I'm writing that out. Only involves the substrate. Only involves the substrate. Right? So what would the rate law be for E1?
K times substrate.
K times the concentration of the substrate. All right, so in the mechanism, let's go through that. So there's one step, and we're going to construct the energy diagram and all that stuff, and we'll talk about the transition state and all of that too. So this is sulfuric acid. Right, and first step is to do a proton transfer. So we end up with an intermediate. Anybody remember what this intermediate is called? This type of intermediate where water becomes my leaving group? And we've seen this a bunch of times since August. It's October now. It's isn't it? hydronium.
Yes, it is a hydronium.
All right. So we have in the first step, proton transfer. And that gets us to this hydronium intermediate. And again, think about what we're trying to do. We want to eliminate OH is a bad leaving group, so that's not going to happen. So here we get to this intermediate, and then obviously water is a much better leaving group, so we lose that and get to this carbocation. All right, where are my alpha positions on the carbocation? Or when you think about elimination, where are the alpha carbons here in the hydronium? Let's start there, since you can still see the leaving group. Where are the alpha hydrogens there?
The one on the right.
Right here. Is that the one I highlighted? Is that the one you're talking about? What
Yeah,
about
I was gonna say the one adjacent, I guess, to the ox. Yeah.
so the carbon that contains the leaving group is here. The alpha sites are always next door, so the carbons that are adjacent. Right. So now I have these protons here and here that I can remove to do my elimination. The question is, what actually does the elimination? Oh, let me put that plus H2O. The question is, what actually does the elimination, right? And so if we take the carbocation, right, we can eliminate either side because it's symmetrical, so that doesn't matter, right? But it can be water, which is here, or it can be the conjugate base. Either one of those can do the elimination, right? So the water can eliminate, or the conjugate base. The water is probably a better base than the conjugate base of sulfuric acid, so we can just use that. But the mechanism doesn't change, right? It's here. So I'm going to just take off, and I can take off either one of these, doesn't matter. There's no geometric constraint for E1. All right, so there's no need for that anti-periplanar geometry that we saw in E2. So if water comes in and does the elimination, I'll get my product here, plus H3O plus the conjugate base, which is probably going to do a proton transfer with that H3O plus and get you back to your start material. Let me not say probably, it will, because the sulfuric acid is catalytic. So anytime you use a catalyst, it always gets regenerated. You never use it up. So this is H2O. So these two will eventually like do a proton transfer with each other and get back to the starting acid. It's always regenerated. So with the E2, I'm sorry, with the E1, again, it follows the same path as the SN1 all the way up until the elimination step. All right, and we know the rate K times the substrate. What does if I ask you to draw an energy diagram for this particular reaction, what would it look like? How many steps? Right, the proton transfer, that's a step. Is that right? To get to the intermediate, the loss of the leaving group, which is the rate determinant step. Let me put that in here, because that's just like SN1. Loss of leaving group is the rate determinant step. That's a step. And then the elimination is also a step. So how many steps is that total?
3.
3 steps. So how many humps should be in the energy diagram?
3.
3. All right, the proton transfer, that's going to be rapid. And it'll get you to that hydronium intermediate. And then the loss of leaving group is going to have a little higher activation energy because that's the rate determinant step. That'll get me to here, to the carbocation. And then the elimination step is here. Right? But this is going to be your rate determinant step, or the step with the highest activation energy, or the slowest step. All right. So for that rate determinant step, what does that transition state look like? What does the transition state look like for the rate determinant step? Anybody? What is the rate determinant step again? If I'm going from the hydronium ion to the carbocation, what does that look like in terms of a transition state?
The addition of a hydrogen atom.
Okay, so look at what we're doing here, right? We're breaking the carbon-oxygen bond. Sorry about that. We're breaking this bond right here. Is that right? To go from that to the carbocation. And that is the substrate that we're measuring in the rate with the rate law. K times the concentration of the substrate, because it's a whole different step. But because it's rate determinant, it's the slow step. That's the step that matters for the reaction, right? So it determines the rate for the reaction. So if I'm just losing the hydronium ion in that step, what would the transition state look like? Remember when we did the SN1, what did the transition state look like for that? Wouldn't it just be a partially broken bond between oxygen and carbon? Did I put that as positive? I should have put a plus. That'd be it. So this has a plus charge on it. Is that right?
Yes.
Yeah. It's just like the SN1. Everything up to the elimination step is identical to SN1, even the transition state, which is just a partially broken bond between the leaving group and the substrate. All right. Let's go back and work through some. Any questions about that before we do something else? So even the solvent, Protic solvents will stabilize that leaving group that's leaving. And so that's a good thing because the leaving group is not always positive. In this case, it has a plus charge, but it's not always a water that's leaving. Sometimes it's some other leaving group. All right, let's go back up here and work through some of these elimination problems now. F already, we did 755. I want you to work through 749 on your own. And let's do A. Let's do C and F. So it's telling us in the question, and I'm gonna cut this out, but it's telling us in the question that these are E2 reactions. And we know that based on each of these bases, right? So this is that tert butoxide, DBU, so it was in the video, diaza, bicycloundecane, very strong base. And then OH, we've seen that a million times, right, as a base. So let's take that, I'm gonna cut it, put it on another page. We'll work through these examples. So let's take A. First of all, where's the leaving group and where are the alpha positions? Those are the two things you have to be able to identify up front to do elimination. So where's my leaving group?
The chlorine.
Chlorine, good. And then alpha, the alpha positions would be next door. So this
The carbon. Yeah.
Yeah. So we're going to get two products. Is that right?
Yes.
All right. So let me. All right. So let's put some hydrogens in. Hydrogens here. That's a CH3. And the base is tert butoxide. So we're not going to go through the mechanism. We've seen that already, right? We can do it for one side over here. This is the base. It's coming in, pulling off a proton. These electrons are going here, and then you're losing your leaving group. So that's one of your products. And then may as well do the other side. Here, the base is going to pull off a proton here. Boom, and then same, you'll lose your leaving group. All right. So with that said, if you have a problem like this where it just says predict the products, right? Really, if you find the leaving group and the alpha hydrogens, you know where the products are going to be. You know what the product is. It's always the alkene, and you should know where to put the double bond. So over here, you'll have a double bond on this side, and then on the other side, you're going to have a double bond here. So you get two different products. So that's one of them, and then the other one is here. All right. Now, the question is, which one is major? Because it also asks us that. Predict the major product using Zaitse's rule. How do we know which one is major? What is Zaitse's rule? We got 14 people here. and one person answering all the questions. What is Zaitsel's rule? And what does it tell us about elimination reactions? $14 out of 25, by the way. Let me say that too. We talked about this on Wednesday. Zaitsel's rule is,
The one that's most substituted is the most stable.
yes. And that the more stable alkene is always going to be our major product when we, if it's the result of an E2 elimination, right? Or E1 or E2, they're both governed by Zaitsel's rule. So we go to here, this alkene is disubstituted. This alkene is mono-substituted. It only has one carbon, one bond to carbon. Everything else is a hydrogen.
So the first one is your major.
Yes, so this is major, and then this is minor. All right, let's do C. I'll just go ahead and cut it. We're not gonna go through the arrows because I want to have time to do some E1 reactions as well. Where's my leaving group? Where are my alpha positions? That's your strategy for solving E2 problems. Look, find a leaving group and then find the adjacent carbons that are adjacent to the carbon where the leaving group is. So my leaving group is what? It's not methyl.
Iodine.
Right? Iodine is my leaving group. And then adjacent to that carbon where the leaving group is, we got carbon here, and then what about that CH3? Is that adjacent also?
I would say so.
It is, right? So how many products are we going to get? If we got 3 alpha sites,
3.
3 products. Right. So again, with knowing where the leaving group is, right, we can put the double bond in, right? Before we even draw the product. We know we're gonna have a double bond here because this proton is gonna get removed by a base. We know we're gonna have a double bond here because one of these 2 protons is gonna get picked off by a base. And then we know also we're gonna have one here, right? Because one of these protons is coming off with a base, right? So when it's asking us to predict the products, that's the strategy. Right now, if it asks for a mechanism, then by all means, you got to go in and show the proton transfer. But since it's all concerted, it's really just 3 arrows. The base pulling off the proton, the bond between the proton and the carbon going, those electrons going to make the double bond, and then the leaving group leaving. So with that top one, that's going to look like this. Right, that's the blue proton coming off. And then you have, if we pull off the red proton, that's my product. And if we pull off the green one, that's my product. So you got those 3 products from that reaction. All right, any questions about it? Anybody not see what I just did? I didn't go through the arrows. We've been through the mechanism enough that you should be able to handle that part and put the arrows in. But are there any questions about the products? Which one is major? This one is di-substituted. It's got 2 carbons bound to it. The other 2 groups are hydrogen. This one right here is tri-substituted. And so is this one. Right, so you really have a kind of a tie between these 2.
So let's say on like an exam and you say list the major products
Mhm.
and we only choose one of the 2. Would that be technically wrong?
No, it's not. Because
Okay.
even with those 2 products, and let me see what the base is for that. I was just OH. Even with those 2 products, one of them, I mean, one of the things is accessibility. How accessible are the protons? And you can see right here, this proton is on a this proton right here is on a tertiary carbon, and then these protons on secondary carbon. So it may be, and when I say a tie, I don't mean that in a literal sense, but they're both tri-substituted. We don't know the percentages, but the fact that the protons that are here on a secondary carbon, that may make those protons a little bit more accessible. And if you're talking about product formation and rate and so on and so forth. But technically, no, you would not be wrong, because both of those would be considered tri-substituted alkenes.
Okay, thank you.
Good question. What's the last one? F. We can do this one up here. Where is my leaving group? Where are my alpha protons? Where are the double bonds going to be in the product? Keep in mind also, the bromine is not a part of the product. It's a leaving group, right? So we don't see that in the product. But I see a lot, I've seen a lot where if someone is drawing a product, they'll leave the bromine there. That's the whole purpose of the elimination, is to get rid of the bromine. All right. So where's my leaving group? Where are the alpha positions, and where the double bonds going to end up?
Bromine's the leaving group. The alpha products are the 2 next to the carbon that's attached to bromine.
So
There's
here,
going to be 2 products.
Mhm.
Yes. And it's going to be the double bonds attached to those 2 carbons.
So the double bond is going to be here.
Yep.
And here, right?
Yes.
That's a given. If those are alpha positions and they have a proton that can be transferred to a base, that's where your double bonds are going to be. Right? So I can just redraw. I'll do the blue one since I got the blue pen already out. So you'll have a double bond here, like that. And then you'll also have a double bond here, like that. Which one is major? You got
The red one.
2 carbons there, and then you have 3 carbons attached to that double bond. So this is major. All right, good. Questions? I know it's Friday, and we're 2 weeks from homecoming, or 3 weeks, something like that, 2.5 weeks. All right. Any questions about that? About anything we talked about with the E2 or E1? We're going to work some E1 examples now, if there are no questions. All right, let's see. What are we doing right here with the E1? So I'm going to take 2 of these and we're going to work through them. And neither of them are trivial. So it's gonna take some time to walk them down. So I'm gonna take these two right here. Because we can introduce, well, emphasize a concept dealing with these carbocation intermediates. All right. So if you looked at B, right, and this is one of the ways to tell if an elimination is E1 or E2 is to look at the reagents. So right here, my reagent is sulfuric acid. So acid, not base. So if there's an acid present and there's an elimination product as a result, then you know that it's E1. Right. So along with that, the fact that you have a pi bond in the product and acid is present, so the pi bond is indicative of elimination. The acid tells you that it's E1 and not E2. E2 has to have a strong base present. So hydroxide, terbutoxide, DBU, something like that. Right. And I actually in the elimination video, if I'm not mistaken, there's a table, a list of bases in that video. All right, let's do the first one. Where should the double bond go? If all things being equal, where's my leaving group and where are my alpha positions?
We're on, well, either one, I guess.
Let's do B. We're doing B. Sorry.
Okay. The OH is the leaving group.
OH, okay, good. It's a bad leaving group, so we gotta fix it up.
Yes.
Which we normally do, right? Protonated, add
And-
something to it. Go ahead.
I'm sorry. And the two carbons that are attached to the carbon attached to the OH.
So it'll be those two that are highlighted. Is that right?
Yeah. Yeah.
Where's the double bond in the product? Is it at either one of those locations? Because if everything was equal, there should be a double bond here. And then a second.
And one there. Oh, so it would be. So it would be on the, how would that?
Let's talk about, that's why I picked this problem. That's why I picked it.
Okay.
That's why I picked it. All right, so let's go through the mechanism of that reaction. So we're doing B. All right, so I'm gonna redraw it. And that is a chiral center, so I'll make sure I honor that. This is that. What's the first step? I need to make this a better leaving group. So the first step is going to be proton transfer. So then I'll get to this hydronium intermediate. And then this is here. All right, now what? What happens once I do that proton transfer? What happened up here when I did the proton transfer?
You lose the leaving group.
That's the next step, and it's the rate determining step. So I'm going to show that a loss of leaving group, which is going to lead to a carbocation intermediate, which is here. This is still here. And there's a hydrogen hanging back here. All right. Now, look at my product. Where would I have to pull a hydrogen from on this intermediate to get this product with the double bond right here? If I want to put a double bond here, where would my alpha hydrogen have to come from?
The other side of that thick line. Does that make sense?
Yeah, so we do have a hydrogen here, is that right?
Yeah.
So it would have to come from there. But as it stands, that's not going to happen. But we have a secondary carbocation, and it's next to a tertiary site. So this is a perfect opportunity for a rearrangement, right? So we can do a Hydra shift. I think we talked about this before. When we were doing the alcohols, the alkyl halides, that was an example that had a hydride shift or a methyl shift, one of them. This is a type of rearrangement. So this is going to come here, and that is going to create a carbocation. Now I'm just going to draw this as a straight line, because once you move that proton, it's going to scramble the stereochemistry. It doesn't stay wedged. So now I have a plus charge here, and then I have an alpha proton here. Right now, the bottom, keep in mind where that plus charge is on that bottom carbon right here. That is already one proton there, right? So now this is a CH2, right? Let's just circle that one and say that's the one that moved. All right. So we do a hydride shift, and that causes the carbocation now to move to here. And this is a tertiary carbocation, is more stable. So now let's just say it's water. Water comes in, takes that, and now you can get to that product. That's the observed product. Which is this. That's the observed product. All right. Questions about that? We've seen this rearrangement before. It's been a minute, but we did see it before when we did the alcohols, the alkyl halides. Like that was one particular problem in there that had actually more than one that had what we talked about rearrangement. But anytime you get a chance to go from a less stable carbocation to a more stable carbocation, you'll see that rearrangement. And it's really not costly as far as energy is concerned, because if you break a CH bond and make it somewhere else, you didn't lose anything. So it doesn't cost any energy for that to happen. Well, it may cost some, but not a lot. Right? What about the second problem? We got 3 minutes left. About the second problem. You think something similar is going to happen there? Look at it's the same type of substrate. Here's your leaving group, alpha, alpha, but you don't see double bonds at the alpha positions. You see a double bond here.
Why
Would it be the
wouldn't you
same
see that?
thing since sorry.
No, you're okay. Go ahead.
No, I was asking, would it not be the same thing since you said that the leading group wasn't really the best leading group?
Mm-hmm. So it's going to go through the same mechanism up to the point of the carbocation. Let's do that. Right? The mechanism doesn't change all the way up to the carbocation. So let's just draw the intermediate. Right? So there's a plus charge here. There is one hydrogen on that carbon. And then you have two methyl groups up here. right? And keep in mind, there's no alpha, even though I highlighted it, there's no proton there. So let me take that highlight off. There's only one alpha position, and that's here. But we don't see that product, right? So here, what can we do to convert that? Because this is a secondary. What can we do to make it tertiary, make it more stable? Right, because obviously the plus charge is going to be here at some point in order to observe the product that we see. Right, so just like we can do a hydride shift, we can also do what's called a methyl shift, the whole methyl group. And let me clarify up here. So a hydride is hydrogen with 2 electrons and a negative charge. So when we move that hydrogen, you notice the arrow starts in between the bond because it's the hydrogen and the electrons moving. So a methyl shift is going to be the same way, right? So the methyl shift is going to be a carbon with a pair of electrons, right? So we're going to move it. We're going to take this one and move it. There is a hydrogen at that site, so that's where my alpha hydrogen is actually going to end up coming from. So I end up here. Now the plus charge is here. And we have a hydrogen here. So that's where the water or the conjugate base is going to come in and do that proton transfer to give me that product. So now this is the product. And anytime you see the product, but it doesn't match what's expected, then more than likely somewhere in the mechanism, some type of rearrangement happened. So that methyl shift is also like a hydride shift. It's a type of rearrangement. Let me move this over. All right, questions about that? Any questions? All right. We're going to stop here. We're 1 minute over, and I'll post this later. And thank you to those